There's a couple lessons here where I want to talk about joint PDFs. Okay, so PDFs where we have two continuous random variables. So it's joint because we're thinking about two different random variables, and they're PDFs because they're both continuous. And in one sense, I'll sing my favorite refrain, joint PDFs are just like joint PMFs, all the basic rules of probabilities for joint events and conditional probabilities. They all just go through the way they always do, but even more so than with conditional probabilities, the symbols can get more complicated with joint PDFs. So I want to just kind of give you an introduction to how we think about those. It is a stretch topic for 200A. Don't worry if you're not feeling like a stretch is what you need right now, you can skip this. On the other hand, I think many of you are more than ready to think about joint PDFs. What I'm going to do in this lesson and the next one is try to get you going with the idea that if you're interested, you can work through the appropriate sections in Bertsekas and Sissiklis. They cover the topic in a really nice, accessible way. All right, so joint PDFs, what are we thinking about? We're thinking about something that looks like this. So it's the joint distribution of two random variables, X and Y. And so that PDF is a function of two variables. Okay, so something that it means is that we need two axes just to graph our X's and Y's, just to specify our events. Okay. So thinking about then what the PDF would be, it's would be some additional dimension coming out of the board here, floating above the XY plane, and the height at which it's floating above would be the value of the PDF. It also means that the probabilities of events are volumes that are above an event defined in the XY plane, and where the height of the volume is determined by the height of the PDF. Okay. So let's just talk about this in terms of our favorite simple example, the uniform random variable. So what we're now thinking about is two random variables, X and Y, where their joint PDF is 1 when X is between 0 and 1 and Y is between 0 and 1. Okay, so we might say it's uniform over the unit square is a way somebody would typically say this. And of course, it's going to be 0 everywhere else. Okay, so what that would look like if we've got X equals 1, Y equals 1, and 1, 1 here. So our PDF is, again, it's floating above this plane at a height of 1 on this square, and it's 0 everywhere else. So it's just plastered down onto the XY plane everywhere else. This is the PDF for uniform joint distribution of X and Y over the unit square. Takes a mouthful to say it all. And if we want to know the probability, say that we want to say that X is less than 1/2 and Y is less than 1/4. This is an example of a joint event here. Okay, so what I'm saying is I want the probability that X is between 0 and 1/2 and Y is between 0 and 1/4. So it's the volume above this area where the height, so the volume is going to be length times width times height here, and the height is given by the PDF here, and that PDF is flat. Okay, so it's, in this case, it's like the volume of a rectangular prism above the area defined by the event that I did not mean to erase there. Okay. All right, so with uniform joint distribution, just like regular uniform distributions, sometimes we don't need a lot of fancy math. We can just kind of reason or work it out with basic geometry. The PDF is uniform over this unit square that has overall volume of 1 associated with it. The joint PDF integrates to 1. And what we might be thinking here, I keep thinking I've got the pointer and I've got the eraser. You know, I do this in real life too, or in person, remember what that's like? Person, I'm even funnier, I can erase with my sweater. Okay, what was I talking about? I was talking about the fact that we might reason that since the PDF is uniform and the event that I'm interested in is 1/8 of the total area, that the probability might be 1/8. Okay, that is indeed true. And it is indeed true that for joint uniform RV, the probability of A is the area A divided by the area mass. And the area mass is, of course, going to be 1. That's only true for uniform random variables. If the PDF that's floating over that XY plane is curvy, then we really do have to integrate. We can integrate as well with the uniform random variable. So I want to use this simple example to sort of show you how that integration works. So again, what we want here is probability that X is between 0 and 1/2, Y is between 0 and 1/4. Okay. So we have to integrate twice. We have to integrate with respect to Y and X. Okay. We have to integrate that joint PDF with respect to both variables. Here's how we do those double integrals. Okay, the way we always do it is we do the inside integral and then the outside integral. And so I'm emphasizing that right now because the fact that I've got dy first, dy is the inside variable, it means that the limits of integration on the inside integral need to be the limits for y here. So let's put them in. So we've got 0 to 1/4 there, and the outside variable is x, so these limits have to be the boundaries of the event on the x dimension here. So 0 to 1/2. Okay. And then we just do them in order. Okay. So 0 to 1/2, 0 to 1/4. My PDF is just 1. Okay, so 1 times dy dx. I might just write it dy dx here, doing the first inside integral. So keeping the outside one there, but doing the inside one. The integral of 1 is, with respect to y, is y, so letting y go from 0 to 1/4, and then keeping the dx that we're going to do there. So that equals the integral from 0 to 1/2 of 1/4 minus 0, just doing my definite integral the way I always would, substituting in 1/4 for y minus substituting 0 for y. So what I get is 1/4 dx. And now doing the integration with respect to x, I get x over 4 from 1/2 to 0. That is 1/8 minus 0. And indeed, the answer is 1/8. So in one sense, nothing different than we would ever do, but lots of wiggly symbols to keep track of, and kind of a need to go one step at a time. Okay. Let's do one more double integral thing, just to convince ourselves that the PDF is valid. Okay. So valid PDF. That means if we integrate over the entire sample space, so letting both x and y go from 0 to 1 times dy dx, does that equal 1? Okay. Well, let's first do the inside integral. Okay, so I'm going to just get y from 0 to 1 x, that equals, I'll write out my steps a little bit more here. So just evaluating the inside definite integral here. This is just substituting y equals 1 and substituting y equals 0 and taking their difference. Okay, so 1 minus 0, and still reminding myself that the outside integral still has to be done. And that is just the integral from 0 to 1 of 1 dx is x from 1 to 0 is 1. Okay. So yes, in one sense, just like what we're doing with univariate PDFs, just looks a little bit funkier when you have the double integrals. I've got a few more things to say about joint PDFs. We'll save them for the next lesson.